In this screencast, we're going to go over some of the concepts related to combustion, which is a specific type of reaction that involves the reaction of fuel with oxygen, as shown in the diagram here on the right. The output from a typical combustion reactor is generally called the flue gas. It can also be called the stack gas. The goals for this screencast are to provide an overview of combustion chemistry, looking at a specific example of methane, as well as go over some specific concepts related to combustion, which are the percent excess air and the wet and dry basis. Examples of fuel sources that are used in combustion often include many sources of fossil fuels. For example, oil is used in a variety of different combustion reactions. Generally, oil consists of high molecular weight hydrocarbons. Alternative fuel is CH4, which is methane, and that's a primary component of natural gas. Also, we have coal, which is mostly carbon, also includes some hydrogen content as well as sulfur. All of these can be reacted with oxygen to form a variety of different products, which we'll look at here in a second. The primary source of oxygen is air, which we know has a composition of 21% oxygen and 79% nitrogen. In the case that air is used as an oxygen source, we can see that nitrogen is the primary component of air, and it's an inert species in this particular class of reaction. In this case, all of these fuels are only reacting with oxygen, so the nitrogen content in air simply passes through the reactor. When these fuels react with oxygen, combustion can either be complete or partial. The significance of complete combustion, all of the carbon content in the fuel is converted to carbon dioxide. The hydrogen in the fuel is converted to water, and if there's sulfur in the fuel, the sulfur is converted to sulfur dioxide. On the other hand, in the case of partial combustion, the carbon content in the fuel is converted to carbon monoxide. We still have the case that all the hydrogen in the fuel source is converted to water. So based on these combustion chemistries, we can take a look at what we would expect to see in the flue gas. On the product side, we're going to see carbon dioxide from complete combustion, carbon monoxide from partial, and water in either case. If we're feeding the air in excess, which is common, though we should also expect to see oxygen and nitrogen in the flue gas, and any unreacted fuel. So in this case, we can see that the products are not the primary reason for running these reactions. The real reason for combusting fossil fuels is to generate the energy that they release upon reaction. These reactions are highly exothermic and release a lot of heat that can be utilized for other purposes. Let's look at an example of these ideas in the case of the combustion of methane. Below we can see two independent reactions for the reaction of methane with oxygen. The first is a reaction of methane with oxygen to form carbon dioxide, which is the complete combustion reaction. The second reaction is the combustion of methane with oxygen to form carbon monoxide, which is the partial reaction. In the example flowchart below, the moles of our fuel and air are both specified, as well as all the products. Because we can see that there's carbon dioxide and carbon monoxide in the stack gas, we know that both of these reactions are in play. We also have oxygen and nitrogen, as well as some methane in the stack gas, so the air must be fed in excess, and the conversion is less than 100%. Based on the moles of each species that are specified, we want to find the percent excess air. The calculation of percent excess air is shown here on the right. We can calculate the excess air as the moles of air that are fed to the reactor minus the air that's theoretically required to consume all of the fuel, divided by the theoretical moles of air times 100%. This equation shows us that the calculation of percent excess air is only related to the amounts of the fuel and air that are going into the reactor. It has nothing to do with extent of reaction or conversion of the fuel inside the reactor or anything about the composition of the output. It is only related to how much of the fuel we have, how much of the air that is being fed with the fuel, and how much air we actually need to consume all of the fuel. In this case, we know that there's 1,047 moles of air going into the reactor, which represents the moles of air that's fed. If we want to find the theoretical moles of air that's required, we need to look at only the complete combustion reaction. Partial combustion does not go into the consideration of the oxygen requirement when we're calculating percent excess air. We are only looking at the primary complete combustion reaction. So based on 100 moles of methane that are being fed, we need to find the theoretical moles of oxygen that are required. Looking at the complete combustion stoichiometry, we know that if we have 100 moles of methane, to react all of it, we need 2 moles of oxygen for every mole of methane that we have, so our theoretical requirement of oxygen should be 200 moles. In this example, we're not reacting methane with pure oxygen, so we should need more air to supply the required amount of oxygen. We can find the necessary amount of air if we consider that air is composed of 21% oxygen. By multiplying our 200 moles of oxygen that we need by a mole and the composition of oxygen underneath, which is 21%, we find that we need 952 moles of air theoretically. Now we know what we have fed to the reactor as well as what we need, and we can use the percent excess formula to figure out what the percent excess is in this case. So plugging in the percent excess is equal to the 1047 moles of air that are fed minus the 952 moles of air that are theoretically required, divided by that theoretical requirement of 952. And when we multiply by 100%, we find that we are feeding air at 10% excess. The last thing we want to talk about that's specific to combustion reaction is the idea of a wet and dry basis. The wet and dry basis is specifically representing the composition of the stack gas. If the composition of the stack gas is expressed on a wet basis, that implies that the moles of water is included. On the other hand, if it's expressed on a dry basis, as you would expect, that implies that the composition of every species is expressed excluding water from the overall composition and overall mole content. In this example, we want to find the mole fraction of carbon dioxide in the stack gas on both a wet and a dry basis. So we'll start with the wet basis first. If we want to find the mole fraction of carbon dioxide on a wet basis, we need the total number of moles of the entire stack gas, including water. So we can simply sum up the number of moles of every species that we have. In this case, for example, we have 70 moles of carbon dioxide, we're adding 20 moles of carbon monoxide, and we're adding the 180 moles of water that we have. If we add oxygen, nitrogen, and methane as well, we have a total of 1157 moles. If we want to find the mole fraction of carbon dioxide, we simply divide the 70 moles of carbon dioxide that we have by the total number of moles on a wet basis, and we find that the mole fraction is 0.0605. If we want to find the mole fraction of carbon dioxide on a dry basis, we need the total number of moles in the stack gas excluding water. This should be the same as the sum of all the species minus the 180 moles of water, or we can simply add every species that's in the stack except for water. In this case, if we take our total of 1157 moles on a wet basis, subtract the 180 moles of water, we have 977 moles of stack gas on a dry basis. If we want to find the mole fraction of carbon dioxide here, we take our 70 moles divided by our 977 moles on a dry basis, and we find that the mole fraction in this case is 0.0716. So we can see that the mole fraction increases a little bit on a dry basis because there's no water in the overall molar content. Expressing the stack gas on a wet and dry basis is unique to combustion. It's important to be able to go back and forth between the wet and dry basis depending on the information that's available. For examples of converting wet basis to dry and vice versa, check out another screencast on these type of calculations.